In this video, we're going to introduce another class of functions, the exponential functions. So in addition to polynomial and rational functions, we now have a third category, exponentials. In the next video, we'll talk about our final category, logarithms. As the name implies, exponential functions contain exponents, but so did polynomial and rational functions. What's going to change is how the exponent functions in the expression. In polynomial situations, the exponents are always constant numbers. With exponential functions, we're going to explore what happens when the exponent is no longer constant, when it becomes the variable in the problem. Since we're going to be doing a lot with exponents, let's review a couple of properties of exponents. Just so we're on the same page, remember, anytime we talk about exponents, we have two major parts, the exponent, which is written as a superscript, and the number it's being applied to, which we call the base. It may be helpful to equate base with big. It's the big number. Our first property involves negative exponents. Negative exponents have nothing to do with making the base negative. Instead, a negative exponent tells us to take the reciprocal of the base. In other words, flip it. So a to the negative x is equal to 1 over a to the x, which means that we send the expression to the denominator, then make the exponent positive. This is also the same thing as 1 over a to the x, 1 over a quantity to the x, where we take the reciprocal, change the sign of the exponent, then apply it to everything. Because the numerator is 1, applying an exponent to it doesn't change it. Both of these notations are correct, so the situation will dictate which one we need to use. If our base is already fractional, then the negative exponent property works the same way, but our base could possibly go from being a fraction to being a whole number. In either case, once we take the reciprocal, the exponent becomes positive. Our next property involves an exponent of 0. It may be tempting to say that a 0 exponent would make the whole expression 0, but that's actually not the case. Instead, a 0 exponent makes the expression equal to 1, regardless of the base. So anything to the 0 power is 1. Keep these properties in mind as we start to look at our new functions. So let's introduce our new function, the exponential function. An exponential function is a function of the form f of x is equal to a to the x power, where a is greater than 0 and a is not equal to 1. A is the base of the function, and in this case the base is a constant number. So when we're talking about something polynomial, maybe something quadratic or something cubic, the base is the variable. The base is what changes over time depending on what we're inputting into our function. Well, in an exponential function, the base is a constant number and the exponent is the variable. So as we plug in a number to our function, the number is actually being plugged into the exponent of the expression rather than the base of the expression. So this changes a lot of things about the whole situation. Most notably, it's going to change the way the graph looks. So graphing is sort of our ultimate goal for any type of function we look at. We want to be able to examine all the aspects that are required to graph. So the graph of an exponential function is going to be quite different from the graph of a polynomial function. A is going to be the key part of our function, however, and there are going to be some specific characteristics for our graph based on what A is. So when A is greater than 1, increasing the exponent on A, in other words, as our input for our function becomes a bigger number, the entire expression is a bigger number. So if our base is something greater than 1, then the higher the exponent is, the higher the output is. If instead a is between 0 and 1, so we specifically said a had to be greater than 0, but now suppose it's somewhere between 0 and 1, increasing the exponent on a gives us a smaller number. So conceptually what's happening here is our base is a fraction. So the exponent represents repeated multiplication. So if we multiply a fraction by itself over and over again, we're getting a smaller output each time. So if our base is something fractional, something between 0 and 1, then increasing our exponent is going to give us a smaller output. So let's look at a couple examples of exponential functions. Our first exponential function is f of x is equal to 2 to the x power. So our base is 2, and as with any exponential function, the exponent is a variable. So for any input we plug into our function, the input is directly put into the exponent. That's what's changing over time. So one thing I want you to keep in mind is although they look similar, this is not the same as f of x equals x squared. F of x equals x squared is polynomial, or more specific, it's quadratic. So what's changing with our input is the base of this particular function. So we change the base and we always square it. With our function, f of x is equal to 2 to the x power, the base is staying constant and the exponent is what's changing based on what we input into the function. So the old school way of graphing is plotting points. So that's what we're going to do here. To get a sense of what this looks like, let's actually plot some points. So we're going to use inputs from -2 to 2, just our integer numbers, but keep in mind you could plug in anything you want. Anything is fair game. So if we plug in an input of -2, we're taking f of -2, our base is 2, and our exponent is -2. Now remember we talked about negative exponents before, so a negative exponent doesn't make anything negative. Instead, it tells us to take the reciprocal. So we take our base, which is 2 in this case, and we flip everything upside down. So 2 becomes a 1/2, and then we change our exponent from a -2 to a +2. So if we simplify all of that, our output corresponding to an input of -2 is going to be 1/4. If we apply an input of -1, we have 2 to the -1 power. Take the reciprocal, our exponent becomes positive, and that simplifies to 1/2. So notice here, because our base is greater than 1, our negative exponents give us smaller outputs. Now what happens as we increase the exponent though? So anything to the 0 power we decided is 1, so this is not an exception. 2 to the first power is going to be 2. And then 2 squared is going to be 4. So as we increase our exponent, our output becomes larger. As we decrease our exponent, our output becomes smaller. So plotting these points, we get a roughly curve-shaped graph. And if we connect our dots, we generate our graph. Now notice, based on how we've graphed this, that our graph is stopped at the x-axis. It's not going to go below the x-axis. Well, why is this? Well, let's think about if we were to keep plugging in more negative numbers. So say we plugged in a -3 or a -4 or anything negative smaller than whatever we plugged in. What we're going to continue to generate is smaller and smaller fractions. So if we plugged in a -3, our output would be 1/8. We plugged in a -4, our output would be 1/16, then 1/32, 1/64, 1/128. You get the idea. It continues on forever and ever. So what's happening is our exponents, or excuse me, not our exponents, but our outputs are getting smaller and smaller over time. They're getting closer and closer and closer to 0. But we will never get to a particular value of x as an exponent that would give us an output of 0. So we get infinitely close to an output of 0, which would correspond to a point on the x-axis, but we're never actually going to reach that point where we would have an output of 0. So our domain is all real numbers. We can plug in any number we want as an exponent, apply it to our base, and we can get an output. Our range, however, is going to be everything from 0 to infinity, but not including 0. So we can get any positive output we want, but we can't reach 0, and we can't get any negative outputs. So graphically, this actually corresponds to a horizontal asymptote at the y, or excuse me, not the y, the x-axis. So this should look familiar. We saw these with rational functions. Rational functions were defined by vertical and horizontal asymptotes. Well, exponential functions also have specifically horizontal asymptotes. So because we cannot find an input that will allow us to have an output of 0, our graph stops at 0, not including 0. So 0 is an endpoint, but it's a non-included endpoint for our range. Let's look at another example. So now our function is f of x is equal to 1/2 to the x. So now we're taking a base that's the reciprocal of the original base we started with. So we're going to graph this the same way. We're going to plug in selected inputs and figure out what the corresponding output is, and then we'll plot the points. So if our input is -2, we're evaluating 1/2 to the -2 power. So again, a negative exponent means take the reciprocal. In this case, the base we're starting with is fractional. So when we take the reciprocal, the base becomes a whole number. In this case, it becomes a 2. And then our exponent goes from being negative to being positive. So 1/2 to the negative 2 converts to positive 2 squared. 2 squared gives us 4, so our output is 4. For an input of negative 1, 1/2 to the negative 1, same thing, we take the reciprocal and make the exponent positive. So it becomes 2 to the first power, which is 2. So notice here our outputs are getting smaller. If we plug in our 0 exponent, always equal to 1, always equal to 1 for any base. We plug in an exponent of 1, it's identically equal to 1/2, whatever the base was. And then plugging in an exponent of 2 for a fraction is double multiplication. So we're multiplying 1/2 by itself, or you can think of it as squaring the numerator and squaring the denominator. So if we square the numerator, we get 1. If we square the denominator, we get 4. So for this particular example, because our base was something between 0 and 1, the lower the exponent is, the higher the output. And then as we get more and more positive inputs, our output becomes a smaller fraction. So if we graph this, here's our points. Notice the points look very similar to the ones we just graphed, but instead of increasing as we continue along the x-axis, we're actually decreasing as we continue along the x-axis. So if we connect these dots following the pattern, we get a very similar shape to what we saw, except it's essentially a reflection across the y-axis. As a matter of fact, that's exactly what it is, and that's related to the fact that 1/2 and 2 are reciprocals of each other. So our domain is still all real numbers. We can plug in any number we want, make it an exponent, and apply that exponent to a base of 1/2. Our range is also 0 to infinity, just as before. So we run into the same problem with this function that we had with the previous one. We can get outputs that get closer and closer and closer to 0, in this case as we increase our inputs, as they become more positive. But we can never find an input such that using that input gives us an output of 0. So we can get infinitely close to 0, but we're never actually going to reach it. So our range is 0 to infinity, not including 0. So again, we also have that horizontal asymptote at the x-axis. However, in this case, based on our particular base, we're approaching it from the right-hand side instead of from the left-hand side. So every exponential function we graph is going to look similar to these two we just graphed. The only thing that's really going to change is the steepness of the graph. So a couple things that are going to be in common for every single one we graph. One, we're going to have that horizontal asymptote at the x-axis. That problem of finding an input that gives us an output of 0 doesn't change based on the base we choose for our exponential. So we're going to have that horizontal asymptote for every exponential function. Another thing that's going to be in common for every exponential function we graph is the point 0, 1. So you may notice this is actually a common point for this one we graphed and for 2 to the x, which we previously graphed. This point is shared between both of them. The reason for that is because we already discussed anything to the 0 power is 1. So as we change the base for our function, it doesn't change the output when our input is 0. So inputting a 0, making 0 our exponent, we're always going to have an output of 1, regardless of what the base of the exponential is. So for any exponential we graph, these are two common features, and the only thing that changes after that is how steep the graph is. Now let's talk about a special exponential function called the natural exponential function. Similarly to the number pi, which we've all seen a lot in different mathematical situations, the number that we're going to call e arises in various contexts. And because we see it so much in math and science, we label it as a universal constant. Essentially, that means in any mathematical or scientific situation, whenever we see pi, we all know what pi means. Well, e is the same thing. So because e is so commonly used in different situations, anytime we see e, we all know we're talking about the same number. We label it as a universal constant, which means that everyone who uses e is using the same number, just represented by this particular constant variable. So the number e is approximately 2.71828, etc., so on and so forth. However, like pi, it's an irrational number, so this is just an approximation of what the number is. Anytime we want to use e in a problem, we can use a button on our scientific or graphing calculator to use it. So this means you do not have to memorize approximately what E is. Anytime we use it, we're going to reference the button on the graphing calculator and use that as opposed to an approximation. So make sure you review those online documents that talk about how to input E into your calculator. So there's a document that has a picture of your calculator showing the buttons you can use, and there's also a video that's going to show you how to input E and some other related functions into your calculator. So let's graph this exponential function. So f of x is equal to e to the x. This is the natural exponential function. So again, because e is a constant number that happens to be irrational, we're not going to approximate and we're not going to be able to use standard algebra to figure out what our different outputs are from our inputs. So this is where you're going to use either your scientific or your graphing calculator, depending on which one you're using. Same inputs though. So for each of these inputs, we're going to input e to that power into your calculator. So e to the negative 2 is approximately 0.14. E to the negative 1 is approximately 0.37. E to the 0, well, you don't actually need a calculator for that. Remember, regardless of the base, anything to the 0 power is 1. So e to the 0 power is not approximately 1, it's exactly equal to 1. Regardless of the base, anything to the 0 power is 1. E to the first power is just e, and as we decided, that's approximately 2.72 if we're rounding to 2 decimal places. And then e squared is approximately 7.39. So if we plot these points, we get the same shape as what we had for f of x equals 2 to the x power. We plot our points and connect them, and we have a graph of the same shape. So again, we have that horizontal asymptote at the x-axis, and we also have the y-intercept at 1. The only thing that changed again is the steepness of this graph. So because our base e is higher than 2, the previous one we graphed, this one is going to increase more sharply. It's going to increase faster than our other graph. If we were to zoom out on this graph, we would see this a little more clearly than we can see it just in a 10 by 10. So our domain is still all real numbers. We can plug in any number we want for our exponent and evaluate, and then our range is 0 to infinity, not including 0. So we've defined our exponential functions, we've graphed a few examples. Now we're going to look at an application of exponential functions. So the specific application we're going to look at is interest. In other words, interest you accumulate on some type of financial-based account. So let's make sure we all have some key terminology out of the way. So principal, when we're talking about the context of an account and an account balance, principal is the original amount we either deposit in an account or borrow from a lender. So it's the original amount we take out on the first day. So we're either putting it into an account or we're borrowing it from someone else. Interest is the amount we earn on our deposit or pay on our loan. So as you know, if you have a credit card or if you have a loan of some type, odds are they're not giving you the money for free. They're charging you for use of their money over time. So the amount that they charge you over time, in other words, the additional money you have to pay back on top of what you originally borrow, this is called interest. So essentially you can think of it like rent. They're charging you rent for the use of their money. This is what we call interest. So in terms of calculating interest, that's what we want to do. So we want to know, okay, based on the principal, based on what we originally deposit or originally borrow, how much are we going to have to pay back in addition to that amount? So there are 3 major ways for calculating interest. Every time you take out a loan, they're specifically going to tell you how they calculate your interest, and it's going to fall under one of these 3 categories. So the first way of calculating interest is called simple interest. Under conditions of simple interest, the account collects interest on the principal only. So in other words, every time they add on an additional amount to your account, they're only basing it on that original amount you deposited or that original amount you borrowed. Unfortunately, this does not happen very often. Typically, they want to make more money than they would under simple interest. So this is why most lenders calculate compound interest. So under conditions of compound interest, the account collects interest on both the principal, again, the original amount you borrowed, and previously collected interest as well. So say they calculate your interest at the end of the year. Well, once they calculate your interest, if you haven't paid it off, they'll add it to your account balance. That means the next time they calculate interest, they're applying it to both the original amount you borrowed as well as the amount they already charged you that you didn't pay back. So the interest compounds on top of itself. Each time they calculate interest, assuming you didn't pay it off over the year, they're actually applying more interest to your account. So under simple interest, every time they add interest to your account, it's going to be the same amount. Under compound interest, each time they add more interest to your account, it's actually going to be a larger amount because they're not only applying your interest rate to your principal, they're also applying it to whatever they previously added to your account. So lenders make more money using compound interest. So in the context of compound interest, there's two ways of compounding or calculating interest. The first, which is the most common, is interest that's compounded periodically. In other words, new interest is calculated at regular intervals during the year. So odds are if you have a credit card, your interest is compounded monthly. So anything you don't pay off over the month on your credit card accrues interest at the end of the month. So they calculate interest on your account 12 times a year. They charge you rent 12 times a year, essentially. Another option is interest that's compounded continuously. In other words, new interest is calculated all the time, whatever that means practically speaking. Now, anytime interest is compounded continuously, that's actually going to generate the highest possible amount of interest they could charge you. The good news is that most lenders do not charge compounded continuously interest. It's actually illegal in a lot of situations to accrue compounded continuously interest. So in most situations, when you have an actual account and they're compounding interest, they're going to compound periodically. So maybe monthly, maybe quarterly. Those are the most common situations. So we've defined our key terms, we understand the basic concepts. Now let's talk about how you actually calculate interest. What are the different formulas applied in each situation? So same scenario, and we're going to define our variables first. So A is going to represent your account balance, in other words, the total amount of money in your account. P represents your principal, either the original amount you deposit in an account that pays you interest or the original amount that you borrow from someone else. R is the annual interest rate. So if you look at the description of a loan or a credit card, it's usually expressed as APR. Whenever we use it in our formulas, we're going to have to convert it to a decimal. So if it's given as a percentage, we have to convert it to a decimal first. T is going to represent time in years. So in other words, it's the life of the account. It's how long we are either allowing someone to use our money or how long someone else is allowing us to use their money. And then if we're compounding periodically, N is going to be the number of times to compound per year. So if we're compounding monthly, N is going to be 12. If we're compounding quarterly, N is going to be 4. If we compound semi-annually, N would be 2. It's also possible we could compound daily. In that case, N would be 365. So we have three formulas, one for each calculation of interest. So simple interest, our account balance is equal to our principal times 1 plus RT. So 1 in this case essentially represents 100%. In other words, it's saying we're keeping 100% of the principal in the account, and that plus RT part, that's where we're actually adding on the interest. So R is our interest rate, so we're taking our rate, which is our annual rate, and multiplying it by the number of years we're going to keep the account. That particular value is applied to our principal, and that multiplication part, if you were to distribute, it would be P times R times T. That's the total amount that's being added on to the account balance on top of the original amount you borrowed or lent to someone. So that's simple interest. Interest compounded in times per year, so compound periodically. Our account balance is going to be P times 1 plus R over N to the N times T power. So same variables except we're adding in N, which represents the number of times we calculate interest per year. 1 functions the same way, so it essentially means 100% of the original principal is going to be in the account, and then the addition that's tacked on represents how we're going to calculate the interest. And then our last situation is interest compounded continuously. So in this case, our account balance is equal to P times E to the RT power. So E was that number we just looked at before. It's called the natural base. So when interest is compounded continuously, as opposed to directly applying an interest rate, dividing it by how many times we accrue interest, we're using the number E instead. So one piece of advice I'll give you here, the hardest part of any problem like this, aside from determining which formula to use, is making sure you use the formula correctly. So I specifically want you to look at the second formula, the one for compounding periodically. Let's think about order of operations for how you would simplify something like this. So suppose you plugged in all your numbers representing all your variables, and now you're trying to simplify everything. You start inside your parentheses. So r divided by n, simplify that, add on the 1. Okay, so now the question is, what do you do next? Well, order of operations says once we've dealt with parentheses, we have to apply the exponent, which means that for this case, you simplify inside parentheses, and then whatever that exponent is, in this case it's represented by n times t, you have to apply the exponent next. One of the most common mistakes I see on problems like this is you've got that number multiplied out front, and so you multiply that by everything before applying the exponent. This is going to completely change your answer, and it's also completely incorrect. So you start inside your parentheses, you simplify that first, then you apply an exponent. Only after the exponent has been applied to everything in parentheses can you then multiply by whatever p is represented by out front. So just make sure to pay attention to that. Order of operations always applies, and it's especially important for a problem like this. So let's look at an example. So it says you take out a $5,000 loan with an annual interest rate of 4% with the entire amount to be paid in 5 years. So we're assuming we don't have to make any payments for 5 years. How much will you owe at the end of 5 years under A, simple interest, B, interest compounded quarterly, and C, interest compounded continuously? So in other words, we're assuming everything aside, how much are we going to owe under the different methods of calculating interest? How is the total amount going to change based on the formula we apply? So I like to approach a problem like this first by sort of diagramming the problem. So any value in the problem that represents something numeric, or any key word that tells me I might need to do something in particular, I like to highlight or underline or box in, whatever works for you. So in this case, the key parts are $5,000. Anything that's a number, chances are we're going to need to use. So $5,000, our interest rate is 4%, and we're paying everything back in 5 years. So those are key parts of the problem. So I'm going to make sure to highlight those before I do anything else. Also, under Part B, I was told that we want to compound quarterly. So I'm going to highlight that as well, because that's also going to be something that's applied into a formula. So before I dive in and write down the formulas and start applying, I like to figure out how I would label these. So remember, we have a bunch of different variables. Each of these numbers is going to take the place of one of the variables. So A represents account balance. A is what we're trying to solve for under each of these situations. So A is our unknown. A is what we're looking for. P is $5,000. So it says we take out a $5,000 loan. That's the amount they're giving us on day one at the bank. So that represents our principal. So P is going to be the variable that represents $5,000. R is 4%. If we convert 4% to a decimal, how do we do that? Move the decimal place, which is right after 4, 2 places to the left. Or alternatively, if you just take your interest rate and divide by 100, you'll also get the correct decimal. So 4% converted to a decimal is 0.04. So that's our annual interest rate. And then T, the amount of time we're going to accrue interest on this account, is 5 years. So T is 5. And then also for Part B, we need to know how many times are we going to compound. In this case, it says quarterly, so for Part B specifically, n is going to be 4. Keep in mind we only use this variable n for that single interest calculation, so n only applies to Part B in this problem. So we've identified all our key variables. We know A is our unknown, it's what we're trying to solve for. So let's calculate interest in each of these situations. So our first calculation is for simple interest. I highly recommend writing down the formula you're going to be using before you start plugging numbers in. That way, if you make a mistake at any point, you can go back and more easily determine what you might have done. Maybe you just plugged a number in the wrong spot. So our formula is A is equal to P times 1 plus RT. I know what P is, I know what R is, I know what T is, so I plug in my numbers. So P is 5,000, R is 0.04 as a decimal, and then T is 5. Now I need to follow order of operations to simplify everything. So I start inside parentheses, and then inside parentheses I have an addition and I have a multiplication, so I need to do the multiplication first. So we're just going to go step by step and do one step at each time. So 0.04 times 5 simplifies to 0.2. Now I need to do the addition. So 1 plus 0.2 simplifies to 1.2. There is no exponent in this case, so I can immediately jump to my final multiplication. So 5,000 times 1.2 simplifies down to $6,000. So that means our account balance based on this principal, this interest rate, and this amount of time is going to be $6,000. So to take it one step further, that means the amount of interest we accrued was $1,000. It's however much money is in the account in addition to the principal, in addition to what we initially took out. So essentially they're charging us $1,000 over 5 years for the use of their money. So now let's look at interest compounded quarterly. So again, our principal is 5,000. Our rate is 4% or 0.04. Our time is 5 years. And in this case, for compounding quarterly, n is going to be 4. So again, write down your formula first. Make sure you have all your variables in the correct spaces. And then plug everything in. Follow order of operations again, so starting inside parentheses. In this case, the first thing we need to do is a division. So 0.04 divided by 4, which is 0.01. Notice I also took a moment to simplify that exponent as well. Once we simplify everything in parentheses, we have to immediately apply the exponent. So you can go ahead and simplify this part, and that's not a big deal. We add on our 1. And now we have everything in parentheses simplified. This is where it's very common to make a mistake. So a lot of people will go ahead and multiply the 5,000 before they apply the exponent. This is incorrect. This violates order of operations. Order of operations says if we have an exponent, that comes before multiplication. So we have to apply the exponent before we deal with the 5,000. Now, when you take 1.01 and raise it to the 20th power, you are going to get a long decimal. It's going to be an irrational number. So depending on what the problem is asking for will determine what you need to round to. Typically, if we're talking about money, we want to round to 2 decimal places. So if you have to round at any point during the problem before the very end, ideally you need to keep maybe 3 or 4 decimal places so that when you round in the end, you won't have any errors possible there. It's also great if you're using a graphing calculator in particular not to round at all. So if you go ahead and take 1.01 and raise it to the 20th power, don't even write down your approximation. Just take that number that you get as your output and then immediately multiply by 5,000. If you do that, you don't have to round anything and there's no risk of any rounding error. So for our purposes, we do need to round just to write down the work, but make sure you keep ideally maybe 4 decimal places so that when we round, it's not going to be a big deal. We multiply by 5,000, and this is roughly $6,101. So notice in this case, our interest was $1,101, so it was more than the interest we accrued under the conditions of simple interest. This is because each time they calculate interest, they're adding it not only to the principal, but they're basing it on what interest they already charged us each year. So that's why our total interest is going to be higher. And then finally, let's do interest compounded continuously. So our formula is A is equal to P times e to the RT. Remember, e is a constant. We're not going to put a number in there. We're just going to use a button on the calculator. So plug in the values for our variables. We need to simplify our exponent. So that's going to be 5,000 times e to the 0.2. So next thing you need to do is e to the 0.2 power. Again, there's some documents online to go and check out regarding putting this into your calculator. So make sure if you've never done something like this before you go and you review that. E to the 0.2 again is going to be an irrational number. We approximate that, that's roughly 1.2214. Then we multiply by 5,000 and we get roughly $6,107. So there's a slight difference between this amount and the amount for compounding quarterly. It's not much, but it is higher. And this is because we're compounding continuously. Continuous compounding will always generate the highest amount of interest possible. So in this case, because our balance was pretty low, our interest rate was pretty low, and the account didn't last for too long, 5 years is not a very long time, there's not a very big difference in how much interest was charged. But as the principal gets higher, the interest rate gets higher, and we keep the account for longer, the difference in each of the amounts of interest for the different calculations is going to be much more pronounced. So if you are charging someone interest, then you might want to use continuous compounding just because you know that's going to make you the most money. However, if you're borrowing money from someone, then you would probably prefer that they use simple interest because that's going to result in you paying the least amount of money. Let's look at one more example. So it says you want to invest $35,000 in a retirement account, and we have two investment options. So our first investment is at 4.8% simple interest for 20 years, and our second option is 3.6% interest compounded continuously for 20 years. So both accounts are going to last for 20 years. What changes in each situation is how we're going to calculate interest and our interest rate. So the first option, we have a higher interest rate, but we're only calculating simple interest. And our second option, we have a lower interest rate, but we're compounding our interest. So just comparing one rate to another is not enough. Because we change how we calculate interest, there's not a direct comparison. So we want to know which option is going to give us the greater return, which one should we choose if we want to make the most money. In both scenarios, our principal is $35,000, and then our interest rates and our compounding change depending on what we're doing. So first option, 4.8%, 20 years. Second option, 3.6% for 20 years. So under simple interest, our principal is $35,000. Our interest rate as a decimal, remember take your decimal or take your percentage and divide it by 100, so 0.048, and the time is 20 years. So under simple interest, using the simple interest formula, we have $35,000 multiplied by our interest rate plus 1. So do the multiplication first, 0.048 times 20. Add 1, that simplifies down to 1.96 exactly. Multiply this by 35,000 and we get $68,600. So this means for an investment of $35,000, we almost double. So double would be 70,000. We're almost there. So we almost double our investment under this particular calculation of interest. So let's see what happens with continuous compounding. So our principal is the same. Our rate has changed to 3.6%, which as a decimal is 0.036. And we're also going to keep this account for 20 years. So the main thing that changes is our formula that we're going to use. Plug in our numbers. Now we need to simplify our exponent first, so 0.036 times 20. So e raised to the 0.72 power. Remember, this is going to be irrational, so you either approximate it and keep maybe 4 decimal places, or you just type it into your calculator and don't erase anything and just immediately multiply. So if we approximate roughly 2.0544, multiply by 35,000, and we're left with an account balance of $71,904. So assuming this is an investment and all other things aside, all we care about is which one's going to give us the greater return, interest compounded continuously is going to be the better option. So even though the interest rate was lower, because we were compounding our interest, we were calculating it on the previous year's worth of interest, we actually made more money in the long run. Let's sum up what we've learned. Exponential functions are functions of the form f of x is equal to a to the x power, where the base is constant and the exponent changes. So as we input something into our function, the input now takes the place of the exponent rather than taking the place of the base. That's the biggest change to go from a polynomial function, which we've seen before, to this new class of function, exponential functions. The domain of every exponential function is all real numbers. You can input any value you want, make it an exponent, and the expression will be fully defined with no problems. The range, however, is 0 to infinity, not including 0. On the graph, this corresponds to a horizontal asymptote at y equals 0, otherwise known as the x-axis. So the reason we have this issue with the range is because for any base, there's no exponent we can raise it to that will give us a 0 as our output. Even using an exponent of 0 is still just going to give us an output of 1. So regardless of what exponent we input, we're never going to get an output that's exactly 0, and we're never going to get an output that's negative. So this gives us a horizontal asymptote at the x-axis, and it also means our range cuts off at 0. We can only get positive outputs for any exponential function. We had a special exponential function, f of x is equal to e to the x. We call this the natural exponential function, and it has the base e, which is a universal constant, which is approximately equal to 2.72. So this is a special number that we see pop up occasionally in mathematical and scientific contexts. We know we have a button on the calculator for it, so anytime we see something with e, we use that button on the calculator. And we know now that exponential functions can be used to calculate an account balance in a financial situation when the account's interest is compounded over time.